originating from the University of Tokyo. So we have, now I'm a little bit in trouble with pronunciation, but Shigeru Chiba.
Perfect.
Was also author of the last paper which was presented, as I've seen it correctly. And yeah, the topic is Bugfox, a trace-based analyzer for localizing the cause of software regression in JavaScript.
Thank you for the thank you for the introduction. Okay, I'm Shigeru Chiba. I'm going to talk about this work. So basically, this is a joint work with a bunch of students and faculty, student on me. But the main contributor to this work graduated last month. This master student graduated last month, so that's why I present this work instead of my master student, Yuefeng. Anyway, so this work is on software regression. And finding a software regression is pretty straightforward nowadays. We can simply run a unit test for every new release. The technique called unit testing is pretty old classic technique, and which is back to it's a best practice back to 1960s, according to the Wikipedia. And because this is a very classic techniques, testing frameworks have been used for a long time, and one of the famous one is the S-Unit, developed by Kenbeck, and the J-Unit is pretty successful tools for Java developed in 1990s. And since then, almost all the languages has similar testing frameworks. So nowadays, running unit testing is one of the best practice of software development. So finding a software regression is easy. But the question is how we find the cause of regression when we actually find the software regression. I don't think it's easy because, okay, you can run a unit test, you can find something wrong. But failed test only tells you that tested function returns a wrong value or wrong side effects. But the question is, which indirectly called function from the top level unit test causes a regression? So if you write unit test for every function, that would be, well, identifying the cause of regression would be straightforward. But the reality is a little bit different. So this is an example we used as a kind of motivating example. This code was taken from some real bug database, which is originally taken from GitHub repository. So this is in JavaScript, written in JavaScript. So this unit test just simply tests map.test.js, and it assumes that it should decode successful when key is null. And the remaining function, the remaining code is like that. It first set up the data, a bunch of data, and calls Haitian.decode with the data. This is so Haitian decode is a function we want to test, and it returns a null. That's okay. And if it returns a different value, where we identify this decode function doesn't work well, it causes a regression. And in this particular case, the cause of the failure is not within the definition, function body of Haitian.decode. The real cause of this bug was in some Lambda function called indirectly called from Haitian.decode. So, well, this is a diff file between the two versions. One version it runs successful, and the other one, new version, which calls a regression. So in this particular case, the originally the change was the if state, the condition for the if statement. At the beginning, it simply checks this, but for some reason, the developer changes this if expression in that way, and that changed how to handle the null case a little bit. Basically, the developer misunderstood the specification of this Heygen protocol and caused a bug. But so the goal of this work is to find, okay, although the unit test fails when it calls Heygen.decode, but the real cause of the regression was not in that function, but that the real cause is in this lambda function is assigned to proto.read object. So it's the location of this source code is very far from the original declaration of Heygen.decode. So that's a goal. By the way, this example was taken from the real GitHub repository, and you might think, why this regression bug is committed to the repository? Because we usually run a test case, a unit test. We usually performs unit testing before committing. So if the developer is reasonable developer, he should be able to identify this new version has a bug. So before committing, he thought he has to fix the bug, but he didn't fix the bug and just committed to the repository, and that's why we found this bug within GitHub history, Git history. Well, this is a side story about the reason why this bug was recorded in the repository was that the guy changed the unit test to pass the code, right? So it's kind of a crazy thing, but you guys are laughing, but I wanted to say that this is a reality, right? Well, we know, everybody understands the practice of unit testing, but not all the developers does unit testing in an appropriate way. Well, originally invented by the people, right? The smart people. But anyway, so in this particular case, this regression was not found by the original committer. He wrongly committed this bug, and later another guy found that, oh, this is wrong. This unit test is wrong. And then he fixed it, or he or she fixed it, and then found, oh, regression happened. But then, this code was, this change was committed a long time ago, so the developer found this bug, got a problem. Where is the real cause of this bug? So the challenge is how to find it. Our idea is pretty straightforward or naive, I should say. So let's look at the return value. So anyway, when regression happens, a function should return a different value. I mean, within the trace of the execution. So our tool Bugfox records execution traces and compare them between the two programs before and after regression. And if a function returns a different value, in this particular case, the original tested function is decode, but the first function get integer returns the same value, but the second call to the read object function returns a different value. So when we compare the execution traces, we should be able to find that. And then we can spot, okay, the cause should be the read object. So that's very simple. Again, some of you might say, that's super naive. And in the reality, is not such a simple case. So the idea is okay, but would not work. There are a bunch of questions, concrete questions. Many functions return different values. So if only one single function returns a different value, then it's easy to spot that function as the cause of the regression. But maybe in real cases, many functions will return different values. So question, which one is the cause? Also, okay, yes, we can record the execution traces, but in real-world JavaScript program is pretty large. So if you naively record all the execution traces, maybe the size of the log will explode, and maybe gigabyte or terabyte. And question is whether it is pragmatic, or not. So our research challenge was to answer those questions. So we implemented this naive idea and made a kind of test database taken from the GitHub and check it really works or not. And of course, this paper was accepted. The answer was, well, so-so, it works. But anyway, so the first author, who is my master's student, ex-master student, developed a tool named Bugfox, because this work was actually consists of the two master thesis work, and the first guy developed a bug bear. I don't know why he named that tool bear, but maybe he loves a bear. So then the second guy named it, I love a fox. So his tool is called Bugfox. But anyway, that's, I guessed. So this is a tool for detecting the cause of the regression in JavaScript. This is only for JavaScript, not a general purpose tool. It records and compares execution traces, and to get the execution trace, this tool automatically translates source code into different JavaScript code, which includes a bunch of logging code to dump execution traces. And after that, it compares them and reports a candidate function of regression. So which data is included in traces, execution trace. So every function, this tool, Bugfox, logs every function call. So that logged data includes a function identifier, which is a name and a source code location and kind of function, because JavaScript supports different kinds of functions like a lambda and function, and so on. And also it records a hash value of a function body. And also it's caller function. And also the value of arguments before and after that call, and also the value also the return value. And this tool also records this object before and after. I mean, the properties of this object. And although those values are encoded by JSON.stringify, although he a little bit modified that stringify because the original JSON stringify doesn't support cyclic objects. But that's a simple thing. It's nice work for master student. It's good practice. But this tool does not record side effects on global variables. That's our engineering decisions, because if we record all the global side effects on global variables, it might be huge. It's easy to make the log huge. For example, JavaScript supports DOM object trees. That's large. So we decided to ignore the value of global variables. So that's going to be our kind of the limitation of our tool. But anyway, when we run the code, the system records all the execution traces, including those data. And then first of all, it aligns two code traces before and after regression. It simply does a depth-first traversal, and it compares every pair of two nodes. The two nodes matches if it has they share the same name, they share the same matching parents, and also they have the same number of elder siblings, and all the elder siblings are also matching. In that case, the tool recognize these two nodes match. So in this particular figure, green means match. Okay, first of all, this tree, circle represents a function call, and edge represents a caller-callee relation. So green means matching, and red means not matching. So the tool first starts with the root node along the depth-first traversal way. And in this case, because the red node doesn't match, maybe with a different name or, well, for other reasons. And then okay, so this one's before and that one is after. So once the tool recognizes this node doesn't match, then it ignores the rest of the trees because maybe execution may be different, totally different. And after aligning, it checks whether the matched nodes are different or not. So it checks every pair of a matched node so that to check whether they have the same argument and they have the same this object, and also the return value is the same. So okay, in this phase, unmatched nodes are ignored. The tool only checks the green nodes, matching nodes, and then it recognizes which nodes are same, which node doesn't change, and which node changes. And then the tool introduces the two heuristics. We developed two heuristics. The first heuristic is to find the first deepest marked function. So the question is, as I said before, not a single node will be different. So the question is which one we have to pick up among several nodes. And the first heuristic is maybe the first different function should be the cause of regression. So it simply traverses the tree in the depth-first way, and the first different node it finds is the cause. So that's the first heuristic. And the second heuristic is maybe the function causing the regression will be frequently called, will be called many times. So it counts the number of calls. It counts the number of occurrences of every different node, and the most frequently called node should be the cause. This tool finds top n functions with respect to the number of calls, and in the case of during our experiment, we use the number n. So the tool finds that the top four frequently called functions, and suggest those 4 functions as a candidate of regression. So that's the things done by the tool. Okay, so this is experiments. So the real interesting question is that this simple, naive, straightforward approach works well. I mean, at least helps the developers to find the cause of the regression. Unfortunately, we couldn't find any real database of regression bugs. We only found the bug database, BugsJS. It's a nice database, but it includes many kind of bugs, not only regression. So the second author, I guess it's the second. He's the second author. Second author manually, not only him, but mainly he manually checks the BugsJS dataset and manually found, okay, he found the 12 regression bugs in this dataset. The regression bugs he found are these bugs. Well, 12 is not a large number, but yeah, we didn't find any database. So I believe this is kind of a contribution. Well, not a big contribution, but that's a very tedious manual work. And then we ran the Bugfox to test whether it can find the cause. Okay, by the way, the Bugfox basically reports 4 or 5 candidates, and we recognize that the Bugfox successfully finds the cause of the bug if the real ground truth is included in those candidates. So the important thing is Bugfox is not to report only one single function. It pop up the 4 or 5. I mean, as a combination of the result of the first heuristics and the second heuristics. Here's the result. So basically, Bugfox could find 10 out of the 12 bugs. Not 100%, unfortunately, but that's the reality. By the first strategy, I mean, first deepest strategy found 6 bugs. So the blue one, dark blue one, was a bug found by the first heuristics. And the rest of the light blue ones are the bugs that was found by others, by the second heuristics. So but the 2 bugs could not find the second heuristics, only, okay, the first heuristics. And here's the execution time and the trace size. The original execution time is about 2 to 24 milliseconds, so it's very quick. But unfortunately, because we have to take a trace, and the implementation was not sophisticated, so it takes us, around 10 to 30 seconds. So it's pretty slow. But within a minute, still within a minute, I think it's kind of practical, reasonable, acceptable. Bug number 1 and bug number 16 are the bugs the Bugfox could not find the cause. But we couldn't see any serious differences between the cases Bugfox can successfully find the cause and it cannot. So as I said, there are 2 cases Bugfox could not find the cause of the bug regression. In the first case, the reason was this regression happens after a very large-scale refactorings. So many functions are changed at the same time. I don't think that's a good way in a modern software development of modern software technique. But because of many functions changes, and actually this regression was caused by the function newly added by the after commit, which causes a regression. So technically speaking, Bugfox could not find that function anyway. So this is the first case. This is the one case. The second case that the Bugfox could not find the bug was bug 16. Oh, by the way, Express is a pretty popular JavaScript web server, web app framework. So in this case, in the second case, the test code deal with lots of randomly generated numbers. It's like a port numbers, IP addresses, timestamps, etc., which changes for every run of the unit test. So in this case, many functions return the different values, and in the reason many functions return the different values is not related to regression at all. So again, Bugfox as a technique adopted by the Bugfox cannot find this case. So that's all. Let me summarize my talk. So we presented the Bugfox, which is a tool for localizing the cause of regression in JavaScript. The approach is pretty straightforward. It compares the execution traces between before and after regression, and it finds a function returns a different value. That should be the cause of the bug. And in the case of a Bugfox, it reports 4 and 5 candidates. And it finds 10 out of the 12 real regression cases we extracted from BugsJS dataset, which was originally extracted from real GitHub repositories. And yeah, it's a simple idea, but I believe I could say it works. So that's all. Thank you very much.
Yes, thank you. And just for the record, I was one of the guys laughing when you showed the example in the beginning, not because it was hilarious, because I've seen this way too often in reality. Are there questions?
Thank you very much. Can you please go back to slide number 18? 18, sorry. Are there any non-nuclear options for addressing these issues? I mean, a nuclear option for the first one is probably trying to do some refactoring, recovery, and separating the refactoring from the non-refactoring bit. I would call this nuclear. For the second one, it seems like maybe a little bit non-nuclear would be to somehow blacklist or whitelist, depending on what you want to call it, certain kinds of types and functions so that you can make certain things go quiet and then focus on things that are still different. Would that help? And do you have any idea about the first one?
Is your question, is there any idea to fix that first case? Yeah, it's a good question. I don't know. For the first case, I don't know. Maybe if we can find some nice heuristics, there might be a chance to spot that the cause of the bug. But actually, basically, we spent most of the time for developing a tool which dumps the execution traces, because the JavaScript, real JavaScript program is pretty complex. But we didn't have time to come up with many nice heuristics, and also the size of our data set was very small. So if we really focus on, I could tell my student, okay, find heuristics to find bug 1 and bug 16. Then we can get 100% success rate. But that's not really scientific, right? So that's why we reported our sort of the state of working kind of progress thing. But yeah, to do that, to go to that direction, we need a much larger data set.
Sort of follow-up question. Yeah, I mean, you talked about the size of your data set, right? Can you make any qualified statement about, you know, how often overall that situation is that you're addressing compared to, you know, on 100% of all failing unit test cases, how often, you know, your tool would help? And maybe an extra question to that, does the inclusion of your tool into the unit testing process create any disturbance, or would it just reliably kick in cases where, you know, yeah, so how is the user experience?
Actually, my student developed this tool as part of the commit process. So he still basically takes sort of a commit. So he takes a two commit ID and it just compares. One of the reviewers said that, you know, this tool has to be run before doing committing, but we expected that you know, new version is committed in locally, and then we can easily run a Bugfox to compare this commit ID and that commit ID, and it finds a bug, fix it, and maybe cancel the initial cancel the commit and in a local repository, and edit the program and fix the bug and recommit, and then push to the main repository. So that's the kind of scenario. So it's sort of should be the part of the you know, commit development process. But yeah, thank you.
Okay, another question back there.
Thanks. That was a great talk, and it's always wonderful when a simple idea just works. That's nice. So,
Yeah, sort of.
so
Not perfectly.
But, you know, but pretty close. So, I was curious if you could say something about, you know, how Bugfox was built, how it was constructed, you know, what the structure of the implementation of the tool is. So.
You mean how to generate a trace data?
Yeah. How did that sort of?
Yeah, I removed the original slide that my student wrote for his master presentation because I think that source code translation is straightforward for us. But basically, he wrapped every function with sort of a wrapper function. He got a AST, and every time he finds a function declaration, he wrapped that function declaration with a bigger wrapper function, and the wrapper function records all the value of the argument and return value before and after. That's it. So it's quite straightforward.
Yeah. No, that's good. Cool. Thank you.
Yeah, and also that's the reason why the tool doesn't dump the global value of the global variable. To do that, we have to do more static analysis, maybe in the future work.
Okay. I don't see further question. Maybe also one from my side. So I personally know three main reasons for regression. Well, the first one, pretty obvious. I change a function, it breaks. Okay, yeah. I've done a mistake. The second one, and you have it on your slide with bug 16, the environment changes or is kind of unpredictable. There it could lead to issues. And the third one is something was always broken, but your environment or other context concealed it or hide it. Do you think you could detect the last case?
Can you repeat the last case?
You always have a bug within your program, but due to some other context, you never face the bug. And then you change the context, and then the bug is revealed. So the real cause of the issue was always there, but always hidden. Could you detect it with Bugfox?
You mean the design problem of test cases, is that right?
Yeah, there might be a test case for an issue. The test case is always right, but not because the functionality is correct or the test case is wrong, but because of the context which kind of, obscured that the functionality was broken.
So you mean a test case was not properly designed, so you can't find test bug. Well, that bug will be, I believe that bug will be found later, and that's why we need this kind of tool, because when we write a code, our memory is still fresh, so it's easy to find, that's wrong, right? I made a mistake. But if the bug was found, let's say, a month later or half a year later, then we need some automatic tool to at least to help. Well, this tool doesn't spot just one function, but it shows a candidate. And checking 4 or 5 functions to see what's going on would be fine. So that's our observation. Thank you.
Okay, then I think that's it. Let's thank the speaker again.